How is the hotspot Hawaii in the middle of the Pacific Plate possible? What are your thoughts beyond textbooks? So the Pacific Plate is quite large, but it's mostly oceanic crust. So it's actually not that thick. It's like, let's say 10 kilometers thick, 15 kilometers thick. Then you have the asthenosphere, and then, well, you have the mantle. So the Pacific Plate doesn't really influence a mantle plume rising up from the core mantle boundary and then through the mantle and more. The plate just is kind of like the final thing that gets in the way of that coming up, and that's why you have the Hawaiian volcanic island chain created by that hotspot. Keep in mind, plumes, based off of our best seismic imaging, it's not just like a single column like this. It's really like a dendritic tree. It's a lot of channels and overlapping branches and more that spread out and weave to create this flow of convection and energy. And there's a lot of ideas as to how they're generated. Most of them are related to core mantle boundary dynamics. So you have the inner core, the outer core. It's where the outer core meets the mantle, and there can be interesting mineralogic things that occur there. And that's kind of the idea with generating mantle plumes, is that there's some sort of natural convection that occurs, possibly from the production of like light elements, that want to rise up, like helium and others. I think there's something to that. There's also, if we're going beyond the textbooks, because that was your specific question, this is interesting. Consider an impact event. You have a large impact, okay? It's going to hit, via the physics that we've modeled, it does seem that there is a pretty good spreading that occurs. So it will hit and then spread out and mix into the surface. But it still is going down, and let's say it's an iron meteorite. I mean, this thing is heavy, folks. Like, the density of iron is high up there versus it's probably 2, 3, 4 times that of oceanic crust. I think the density of iron is like 7 or 8 grams per cubic centimeter. Basalt is about 3 to 3.3. So you're going to have that thing sink down, and now you're creating this downward convection. With time, I would not be surprised. And it's also, of course, putting a lot of heat in, right? A tremendous amount of heat just through the impact. Kinetic energy being converted to, all of a sudden, like latent heat energy. So, boom, that's going to create this convection. I bet some of the hotspots on Earth and these mantle plumes were created from past impacts. And once that happened, and later on it's in its history, right? Because during the accretionary phase, you have a whole bunch of this. The whole Earth is churning. But later on, then you get that oddball out to hit, and then you have that whole sequence. If you have convection going, it may just start to maintain itself, especially given a geologic regime of plate tectonics where there is active convection occurring and the whole system still being energized by the sun and radioactive decay and more. So once it gets going, it may not necessarily stop quickly. This is all geologic time. So if we're going beyond the textbooks, I think that there's probably something to that, at least for some of the hotspot / mantle plumes for Earth. And a specific keyword that you could research and like type into Google, let's say, and research into would be drip tectonics, DRIP tectonics. They haven't connected that with impact events, the official researchers, but effectively describing what that's about. So that would be a good place for you to start.